So in our previous versions of understanding the regression model, we had a very simple equation. Test scores were equal to a linear function of the student-teacher ratio. So our student-teacher ratio was our main explanatory variable. But we might easily ask the question, why don't we have a more complicated model of the determinants of test score? For example, have test score depend on both the student-teacher ratio and the percent of English language learners who are in the district. So EL underscore PCT is the percent English language learners. So in this model, the student-teacher ratio affects test scores, but also the percent of English language learners in the school district affect the outcome of test scores. Now, we intuitively understand that outcomes are influenced or affected by more than one factor, more than one variable. So it's not hard for us to imagine that both the student-teacher ratio and the English language learners in the school district, that both of them are determinants of the test score. And we also understand that the student-teacher ratio and the English language learners in the school district might be correlated. And schools with lots of English language learners might have higher student-teacher ratios. So if we go back to our old equation, if we estimated this, test scores equals 698 minus 2.2 student-teacher ratio, we could ask the question, well, how do we know whether that decline, right, that negative relationship between student-teacher ratio and test score that we estimated and saw in the data, how do we know whether that's due to the student-teacher ratio or to the percent English language learners? Since as the student-teacher ratio goes up, we might reasonably imagine the percent of English language learners is also going up. So we see how our basic regression has a problem that when we're attributing the effect of changes in the student-teacher ratio, we might call it an omitted variable. We have an omitted variable, the percent of English language learners, which is also varying like the student-teacher ratio in the same direction and affecting the outcome of test scores. So we have a better model then. Why not explicitly include the percent English language learners in our model and estimate a coefficient that tells us how much the change in English language learners affects the outcome of test scores. So when we estimate this model, we're going to interpret the coefficient beta 2 that we estimate as the effect of a change, a 1-unit change in English language learners on test scores, holding the student ratio constant. So we're always going to say that. At the beginning I'll insist on it, and then of course later as we go on we can assume that everybody understands that's what we mean, that we're holding the level of the other variable constant when we interpret this coefficient. So we'll interpret it as a partial effect. Likewise, we will now, once we have more than one variable in our regression equation, we will interpret beta 1 as the effect of the student-teacher ratio on test scores holding the other variable, in this case English language learners, percent, constant. So it's the partial effect of the student-teacher ratio. And you'll recall from your other classes, in particular microeconomics or in macroeconomics, you probably came across this Latin phrase ceteris paribus, which means holding everything else constant. So this is just another application of that idea in economics of estimating or thinking about the partial effect of something, holding other variables constant conceptually. They may not be constant in real life, but conceptually we can think of holding them constant. So again, just for those of you who remember your calculus, we're talking about a partial derivative. So the partial derivative of test scores with respect to the student-teacher ratio is the partial derivative of this regression equation with respect to the student-teacher ratio. And that's going to be equal to beta 1. So that's the sense that beta 1 we interpret as the partial derivative. We're holding the English language learners constant. And if we do the take the partial derivative, then we notice this has three terms, 1, 2, 3. And so we take the partial derivative of the sum is equal to the sum of the partial derivatives, but beta 0 doesn't vary with the student-teacher ratio, so that's equal to 0. Beta 2 times the English language percent we're assuming doesn't vary. That's our conceptual assumption, that it doesn't vary when we ask what the effect would be of a change in student-teacher ratio holding English language learners percent constant. So that's equal to 0. So the coefficient that we estimate then is the partial derivative of beta 1 student-teacher ratio is beta 1. So the partial derivative of test scores with respect to student-teacher ratio is indeed equal to beta 1. Now we're going to estimate the beta 0, beta 1 hat, beta 2 hat, the estimates of our coefficients, exactly the same way. We're going to choose values to minimize the sum of squared residuals. The sum of squared residuals is exactly as before, the difference between the actual value of y and our predicted value of y for each observation. So the sum is going from I equals 1 to n, however many observations we have in our sample. In the test score case, it's 420. And so the residual, right, is yi minus beta 0 hat minus beta 1 hat xi x1i minus beta 2 hat x2i. We could, of course, have a third variable, a fourth variable. We can, there's in some sense no limit as long as we have a lot of data. There's no limit to how many variables conceptually we can include here. So that's it for this short introduction to multiple regression.